All right, so we're going to talk about solubility today, which has to do with dissolving. And this is the last of the physical properties that we're going to discuss right now. Except for gases, we're going to add one more thing that we can look at specifically for gases in our next unit. Solubility is also something that plays an important role when we talk about chemical reactions in the second semester. So this isn't, again, a standalone topic. Solutions and solubility are crucial for chemical reactions, and everything that we're going to look at today has some impact on that when you come back to it in the second semester. But just a quick review. When we talk about solutions, meaning something is dissolved in something else, solutions are homogeneous mixtures. All right, so breaking that down and reviewing, this all comes from the classification of matter notes at the end of Unit 1. So if you want to go back and review that stuff, if something's not clear, that's where you'd find it. A mixture means that I have more than one substance put together, right? They're physically combined, meaning that they're in the same space, so in the same container, for example, but they're not transformed chemically. And so simply put, when I mix things together, I still have those things. Nothing new has been formed, and the things that I mixed have not been consumed, which means I can separate them again. And so like most physical changes, I can reverse the dissolving process. So that's true of all mixtures. Now for homogeneous mixtures specifically, the mixture has to be uniform, meaning that it's exactly the same everywhere. Every drop of the mixture is exactly the same as every other drop. There's no different parts to it. Heterogeneous mixtures have different parts, and I'll highlight that with an example in just a minute. Another way to say that something is homogeneous is that there's only one phase. You don't see different phases in there. You can only see one overall phase that contains all the materials. Okay, so homogeneous mixtures are called solutions, right? And you may think, well, why do we have these two separate terms for the same thing? Well, it's because scientists used to believe that there was a second kind of homogeneous mixtures. And then when we got more powerful microscopes, we discovered that it wasn't actually homogeneous, that it was heterogeneous. You just can't see it with the naked eyes. Those things are now called colloids. That's not important. We're not going to study heterogeneous mixtures. But there used to be two kinds of heterogeneous mixtures, and now there's only one. So homogeneous mixtures are solutions, and solutions are homogeneous mixtures. So the terms are interchangeable. Now, let me give you an example of what I mean by homogeneous, and then I want to talk a little bit about some basic vocabulary quickly before we get on to the work. All right, so when we say there's only one phase, the example that I constantly use about dissolving something, I used it last week too, is salt water. This is a very simple example. You could also do sugar water if you want to. If I dissolve salt in the water, right, stir it, it seems to disappear. And so I don't see a separate salt phase and a separate water phase, but instead I see one salt water phase. Same thing if I dissolve sugar nicely in, say, iced tea. Right? And then I don't have a separate sugar phase and a separate tea phase. I have just one phase, sweet tea, which of course is a Southern delicacy. Now, on the other hand, if I put sand in water, pour sand in water, stir it as long as I want to, it won't dissolve. And then I'm going to be able to see two different parts, the sand part, which is solid phase, and the water part, which is liquid phase. So that would be a heterogeneous mixture. I can see two different phases, different parts. With the salt water or the sugar water, I can only see one thing, and so it's uniform everywhere. Right? Basic terminology here, and again, don't agonize over this. I've seen some students get bogged down in the vocabulary here. This is not the most important part of what we're doing, but I just want you to be able to understand the terms when I use them. And there is a simple way to do that. Two things have to be involved in any homogeneous mixture or any solution, and there can be more than two. So I can have multiple substances dissolved in the same solvent. The solute is the material that gets dissolved, and the solvent is the environment. The solvent is the base for the solution. Now, in our class, the solvent will be water. Everything that we do has water as the solvent. So that makes it very simple to understand these terms. The solvent is water, and the solute is whatever you're dissolving in the water. right? But if you go beyond this class, I want to emphasize this, there are many solvents. Water is far from being the only solvent, and there's plenty of things that don't dissolve in water. And so if I want to dissolve something that won't dissolve in water, then I need to go get another solvent. So there are many different solvents out there, especially if you go on to organic chemistry at some point in your career. So just understand that what we're doing with water as our only solvent is a very simplified version of this. So then salt would be the solute that dissolves in the solvent water, right? But I want to also point out to you that while we're doing that, it's easy to form the misconception. If water is our solvent and you begin to visualize it that way, it's easy to form the misconception that solvents have to be liquids. They do not. Solvents can be gases. That's very common. So for example, with dry cleaning, you use gases to dissolve dirt and oils that are in clothes, right? That's why it's called dry cleaning. And in fact, air is a solution. The air that you breathe, the air around you right now is a solution. What is the solvent in the air? It's nitrogen. Nitrogen gas is 79% of our air. And what's dissolved in the nitrogen or the solute? Oxygen gas, 21% oxygen gas, and also other things, right? So there's carbon dioxide, there's other substances that are in the air as well. But the base, the environment for the air that contains all the other things that are mixed with it is the nitrogen. So the nitrogen is the solvent in that case. Air meets all of the qualifications that we just mentioned for a homogeneous mixture. It's the same everywhere, right? We don't go to one place and it's 19% oxygen and another place and it's 23%. 21% everywhere. So the mixture remains exactly the same no matter where we go. A very fancy word for the dissolving process is solvation, not to be confused with salvation, which is a totally different process. And I want to briefly just give you a visual for what happens when we're dissolving something. But the key words are in the first bullet point under that term: surround and separate, right? And so the solvent, water, surrounds and separates the particles of whatever's being dissolved in there. Now, I want to remind you, even in the liquid state, there's space between the molecules. So when I look at liquid water, even though it's fairly dense, there's still some space between the molecules. When we think of molecules as being round things can't fit together perfectly and occupy all the space. There's also other factors that we're not talking about right now. So there's space between the water molecules, and I can put other substances in those spaces, which I'll show you an animation for in just a moment. There's an interesting implication of that as well. So when I dissolve something in water, the something is going into the spaces between the water molecules. The particles of the something, the solute, are surrounded and separated. Let me show you a little animation for that, and then I'll talk about the really important implication of that, which leads to most of our work here today. All right, so I've got water in a beaker, and I'm going to drop salt in there. It's an interesting representation of salt. It looks like a sugar cube if you've ever seen one, but it's meant to be one single grain of salt. So if you've ever looked closely at salt grains, they're cubic in shape, and so that's what we have here. Obviously exaggerated. NaCl, sodium chloride, is the formula for salt. If we look down on a particle level, what we see is sodium and chlorine particles fixed together, and the water is able to go in and surround those. And by surrounding those, then the particles fit between water molecules, and the solid is then spread out throughout the entire water. So when I put salt in water and dissolve it, all I've really done is separate the salt into its smallest particles and then spread those particles out evenly. And that's what uniform means, evenly spread out throughout the solution. Then I have only one phase. So I no longer can see a piece of salt and then liquid water, but instead I have salt water. That's what the dissolving process involves. And again, surround and separate are the two really important terms there. Okay, so the implication of that, though, if there's space between the particles and I'm fitting my solute into the space between the water molecules, some things can increase the space between the water molecules. And in particular, temperature can increase the space between the water molecules. So we'll come back to that thought in just a minute. When I use the word solubility, which is what we're talking about, the physical property called solubility, which is a characteristic of a material that we can look up, solubility can be a yes or no thing. So like I could say, is it soluble or is it not soluble? Or insoluble is the term there. So this is sort of an all or nothing way of looking at solubility. There's another way we're going to look at it in a minute. Right, so we have what are known as solubility rules, and I can look these up. It's like a little logic puzzle that you have to work your way through. So we're going to practice it together in just a minute. But I can look up and see, is a particular substance soluble in water, or is it insoluble in water? So it's a yes or a no question. Okay, so we're going to talk about these substances here real quick, and I'll call them out so you don't need to like have this written down or anything. But what I want you to do is navigate to the solubility rules in your reference tables. Don't worry about the entry number 5. That's an old thing I keep forgetting to take out of this. So in your reference tables, find the solubility rules. They're after the periodic table in there. I'll show you on my copy in just a minute. And we're going to look up these 4 substances in the solubility rules, and we're going to determine, are each of these soluble or insoluble? Again, I will call these names out, so don't feel like you have to have them memorized there. Let me get to the reference tables again. All right, so the solubility rules are on page 6 here. All right, there's the solubility rules. It's that small little chart. That's all that we have. If you look in some bigger references, you can find more. And remember that this only has to do with water as the solvent, right? If I had a different solvent, there'd be a whole different set of rules. And so to be comprehensive, it actually takes a lot of different charts, which is why I'm going to show you something else in just a minute that can be very effective. Right, so we're going to look up our 4 substances in here. And all we do is we look up the names of the chemicals. Notice this is all names, not formulas. We look up the names of the chemicals, and we have a table that says these are soluble, and we have a table that says these are insoluble. Right, and so my first substance is calcium chloride. Now you may not find every name on there. Typically, they are arranged by what you might call the last name of the chemical, the second element that's present. So when I say calcium chloride, I'm going to look up chloride first. That's not always true, and sometimes you can find both parts of the name in the table, but we're looking at chlorides. Right? So all chlorides are soluble. Notice how it works. So this is under soluble, and it says all chlorides. There's 3 exceptions, so be careful. What would it mean if it's an exception to being soluble? Well, that would mean that it's insoluble. Right? We'll get to that in a minute. All right, so all chlorides are soluble except silver chloride, lead chloride, and mercury chloride. So those 3 are not. But calcium's not one of the exceptions, and so that means calcium chloride is soluble. Right? And stop me if you're not sure about any of this, the way that you reason through this a little bit. Like I said, it's like a small logic puzzle. Our second chemical is magnesium carbonate. The carbonate is over here. Right? All carbonates are insoluble, with a few exceptions, but we're not one of the exceptions. So all carbonates are insoluble, and so that means magnesium carbonate is insoluble. If you're not sure about the group 1, group 2 stuff, don't worry about it. That's periodic table things that we're going to cover down the line, so you'll get there before you need this for greater detail later on. All right, so calcium chloride is soluble, but magnesium carbonate is not soluble. Let's look at our other 2. Silver bromide. All right, so bromides are right here with the chlorides, right? And all bromides are soluble except silver, lead, and mercury. So silver bromide is an exception, and that means that it's insoluble. And so that's how the exception works. If it's an exception to being soluble, then it's insoluble. If it's an exception to being insoluble, then it's soluble. So you have to kind of work through this. It's almost like a double negative in some cases. Finally, ammonium acetate is our last chemical. And you can actually see both of them. They're right side by side here. So things that have ammonium in them and things that have acetate in them are always soluble. There's not even any exceptions there. So that's a universal rule. Anything that starts with ammonium or ends with acetate is going to be soluble. And so ammonium acetate is soluble. That's how solubility rules work. And this is just a brief introduction. I can't emphasize this enough. We're not even going to practice this part in the packet. I just wanted you to see this because it'll come up later on in the year. And that way you'll be a little bit more familiar with it. It turns out that in chemical reactions, there's a reason why we sometimes need to find out whether something's soluble in water or not. Does anybody have any questions, though, about this really brief introduction to the solubility rules before we head on to the more important topic? Okay, all right, so that's all we're going to say about solubility rules. What's really important now is to talk about the numerical value of solubility. So that's our main goal for the rest of the day today, and this is what you're practicing in the packet. So solubility, as I just said, can be a yes or no thing. It's soluble or it's insoluble. But solubility can also be a number, and that's what we want to focus on. When solubility is a number, what that's telling you is that that's the maximum amount of solute that can dissolve in a standard quantity of water. All right, so I want to talk about the standard quantity of water first. You'll see it in just a minute. But our standard amount of water for all solubility purposes is 100 grams. All right, so when we talk about the number for solubility for a particular substance, what we're saying is how much of that substance can dissolve in 100 grams of water. So that's our basis for comparison. Our standard is always 100 grams of water. If you have a different amount, you have to calculate. So you need to scale up or scale down. And we'll talk about how to do that in just a minute. Right? If I have the maximum amount dissolved and I can't dissolve any more, right, then that's called a saturated solution. Okay? A saturated solution contains the maximum amount. And that's what we're getting ready to talk about, David, is temperature. Pressure doesn't affect this. It only affects it for gases, but temperature does. And we're coming to that. Good question. Right, so saturated is a solution that has the maximum amount dissolved. The way it looks, if you have a saturated solution, if you add any more, it won't dissolve. It'll sink to the bottom. No matter how much you stir it, there will be excess on the bottom. There's a term for that excess that we'll come back to another time. Right, so saturated has dissolved the maximum. Anything less than that, though, and we call it an unsaturated solution. An unsaturated solution has room for more to dissolve. Right, so if I stir a little salt in water and it dissolves, I stir a little more salt in water and it dissolves. I keep stirring more and more salt into the water. Eventually, I'll hit a point where I've filled up all the spaces between the water molecules with as much salt as they can hold. And when I reach that limit, then no matter what I do, the more salt I add, it will just sink to the bottom and it won't dissolve in there. At that point, then you actually have a heterogeneous mixture because you have two phases. If I have less than the maximum, though, it means I can dissolve more. And that's a very general term. Unsaturated is a wide range of things from 0.1 all the way up to whatever the maximum solubility is. All of those are considered unsaturated. Now, under very rare circumstances, we can actually get more than the normal maximum of something to dissolve. When that happens, it's called supersaturated, but it has to have very specific conditions. And so although we'll talk about it a little bit, this is something that doesn't happen very often and almost never in your everyday life. There's one exception. So if you've ever made candy at home on a stovetop, then you've actually made a supersaturated solution. If you ever had rock candy, that's how rock candy is formed. So if you dissolve sugar in water and then gently heat the water up, you can actually get some of the water to evaporate from it without releasing any of the sugar. And so you can create a syrup, a supersaturated solution of sugar. But if you disturb it at all, then all of a sudden the sugar will solidify. And that's how rock candy is made. You have a super saturated solution, and then you drop the stick or the string in there, and it disturbs the solution. And immediately, all of the extra sugar gloms onto that and solidifies. So super saturated solutions are really unusual, and they're really delicate. And so it's not something that you're going to see very often, and we'll only briefly talk about it. All right, so as I mentioned, and as David was asking, the solubility of a substance varies with the temperature. And this is what I was mentioning earlier. If the solute is going to fit into the spaces between the water molecules, if I heat the water, it will expand, which means more space between the molecules. And so if I heat water, I can dissolve more material in there, as long as we're talking about a solid. And so there's an important second thing here, which I want to mention. I don't have to just have solids dissolve in water. We can also dissolve gases in water. So for example, how do aquatic creatures breathe oxygen? Well, they absorb it from oxygen dissolved in water. So a gas can dissolve in a liquid as well. Of course, if you've had carbonated soda, that's the same thing. The carbon dioxide dissolves in the water in the form of carbonic acid, right? Gases are the opposite of solids. So as I heat water, I can dissolve more solid in the water. But as I heat water, I actually dissolve less gas. And if you've taken biology and you've talked a little bit about aquatic environments in any of your previous science classes, and you may have learned that cold water is more supportive of aquatic life than warm water is. And that's because colder water can hold more oxygen. So the colder the water is, the more gas can dissolve. But the warmer the water is, the more solid can dissolve. And so there's an interplay in our oceans, for example, between oxygen content and salt content, depending on the water temperature that we have, which is far more detailed than we need to know for this. All you need to know is this fact. Gases become less soluble as I heat the water, but solids become more soluble. So how do we account for all these different temperatures and make sure that we can find the correct value, numerical value? Well, we use a solubility graph, sometimes referred to as a solubility chart, but I think graph is the better way to look at it. Right, so let's look at a solubility graph. Right, so this one has multiple substances, and this is something you'll need to get used to. It's not very efficient for us to make one graph for every single substance. So when you look up solubility in a reference of any kind, a reference book, you're going to find graphs with multiple substances on there to save space. And so that's what we're getting used to here. So I can actually have 1, 2, 3, 4, 5, 6, 7, 8, 9 different substances represented on here. Each of them has its own curve, right? And these change with temperature. So on the x-axis is the temperature of the water that we're using. And as you can see, nearly all the substances increase their solubility as the water warms up, right? All of these go up from left to right, except for one right here that actually decreases, right? And that's what a gas would do. This doesn't happen to be a gas, but a gas would decrease in solubility, right? So there's two different things that I look at, of course, x-axis and y-axis. On the x-axis is the temperature of water, and on the y-axis is the amount of solute that will dissolve, right? And so I just have to match those up. Each of the points represents the maximum for that temperature. So if I look at NaCl and look at 10 degrees, right? Let me get my little pen up so that I can mark this for you and make sure everybody sees it, right? At 10 degrees, we read up to the NaCl graph, and right there is the point that we're talking about. So that point represents the maximum amount of NaCl that can dissolve in water at 10 degrees Celsius, right? And then if I go over here to 90 degrees, read up the 90-degree line and match it up with NaCl, this point is the maximum amount of salt that can dissolve at 90 degrees Celsius. And so you see we can dissolve more in warmer water than we can dissolve in cold water. Not all that much more for salt. And I don't know if you've ever made salt water at home for like a sore or oral surgery or something like that. And people will tell you to boil the water. You really don't get much more salt in the boiling water than you would if you just stir it at room temperature. So it's probably not worth the effort. Some substances do, but not salt. And that's an important point here. Every substance that we might dissolve in water has a slightly different interaction with water. And so each substance has its own unique curve with its own unique shape. which means that we could use these to identify substances if we needed to. And that's coming up on your homework as well. All right, so reading these again, at 10 degrees Celsius, I go up to NaCl, and then I take this point and extend it over to the y-axis. And that maximum amount is about 35 grams. Right? So at 10 degrees, I can dissolve about 35 grams. Now remember, we're talking about water. And our standard amount of water is 100 grams. So don't let this distract you over here. All this is saying is that we have the standard amount of water. So that's just the label on the axis that says we're dissolving this in 100 grams of water. Right? The number is the amount of solute that will dissolve. Right? So that's 35 grams at 10 degrees. If I go over to 90, it increases to about 40 grams. So 40 grams of salt will dissolve there. So all I have to do is take the temperature, go up to the substances curve, and then read that value off the y-axis. And it tells me what the maximum is. Again, that maximum is called saturated. Right? So if we have a point on the curve, then we have a saturated solution. Anything less than that maximum would be unsaturated. And in rare cases, if it's above the maximum, then we would call that supersaturated. So that's a quick overview of how the solubility curve works, but I think it's a lot better if you actually do things. This is a learn by doing topic in my experience. So I've got a couple examples for you here in the PowerPoint, and then I'm going to turn you loose to work and ask questions in your packet. Yes, absolutely, David. And even solids can dissolve in other solids. It's called an alloy. So the state of matter doesn't have any impact on ability to dissolve. It's just the two materials. The two materials determine it. All right, so each curve that we have represents the maximum, all right? And that maximum is the amount that will dissolve in 100 grams of water, right? Oops, sorry, hit a button. Remember that for water, 100 grams is the same as 100 milliliters. So just in case you see that in a problem, I don't think I have any problems for you that have that, but the density of water is 1, and so that means the mass and the volume are the same, okay? And then the amount of solute is saturated if it's exactly on the curve, right? If it's below that, less than the maximum, it's unsaturated, and if it's above that, it's called supersaturated. All right, so let me go through one example with you here, right? Here's my problem. I have a saturated solution of KNO3, right? 100 grams of water at 20 degrees Celsius, right? So I need to find out how much can dissolve there, and I'm going to go to the graph and read that off. Right? Then I'm going to heat that up to 50 degrees, which means I can dissolve more because I've heated the water up. So then the question is, how much more can I dissolve? So I need to go back to my graph and I need to look these up. At 20 degrees, what is the solubility of KNO3? And at 50 degrees, what is the solubility? And then we can find the difference between them. All right, so let me go back to the graph here. KNO3 is the green curve on here. That's honestly one of the more challenging things, is just making sure you read the labels right and you get the right curve, because there's a lot of information on one of these graphs. Okay, and then I'm going to take it at 20 degrees, right? So at 20 degrees Celsius, what is the solubility of KNO3? Well, 20 degrees hits the curve right here at this point, right? So that's pretty much exactly 30, right? So I take 20 degrees, trace it up to the KNO3 line, and then read off the value there. 30 grams will dissolve at 20 degrees. Then I'm going to warm it up to 50. So I go up here, and you can see the solubility has gone way up. It's much higher at 50 degrees. So there's our point on the line. So again, reading the temperature line up until it interacts with the substance's curve. And that value is 88, 87, something like that. There's going to be some interpretation here. So two different people might see that point slightly different. That's okay. All right, so I started at 20 degrees. I could dissolve 30 grams. When I heat it up to 50, I can dissolve 88 grams. All right, so how much more? Well, it's gone up by 58 grams. I can dissolve 58 more grams by heating the water up. So that's a pretty extreme example. KNO3 and CaCl2, they both increase dramatically in their solubility. Not every substance does that. And that's the answer to your question in the chat, David, as well. So as you see, as we increase the temperature, for liquids, it's the same as for solids. So for example, alcohols dissolve real well in water. And again, when you warm it up, it increases that. Okay. All right. So that's an example. Any questions about that example before we do one more? All right. There we go. All right, so I have 4 questions for you here, and on this slide you have the chart as well. Okay, so I want you to answer these 4 for yourself. I'm going to give you just a few minutes while I take the attendance to look over these, and then we'll go over them. And following up on your question just a little bit more, David, while the temperature interaction doesn't really depend, there is interaction between 2 substances. So as I said quickly earlier, whether 2 substances will dissolve or whether one substance will dissolve in another depends mostly on the 2 substances. And then temperature just affects the amount that will dissolve. So for example, alcohols will dissolve in water, and then if I warm the water up more, will dissolve. And so that's the same way that it works for solids in water. Hopefully that thoroughly answered your question. Yeah, that's a really good question, David. When it comes to liquids, it's somewhat arbitrary. Typically, if water is involved, we assume that water is the base in the solvent. But it's more of like, what did you start out with? You know, did I put alcohol into water or did I put water into alcohol? They're really, that's what makes them a little bit unique to think about compared to solids in liquids or gases in liquids. But the same thing is true with alloys of metals. If I can mix 2 metals together and get their properties combined, so like brass, for example, is a mixture of copper and tin. It's an alloy. And then you ask, well, which one dissolves the other? Typically, whichever one you have more of. I mean, whichever one you have more of is what you would consider the solvent. So yeah, that's a thorny question there. All right, so let's look at the answers to these questions and make sure that everybody understands how to find these, and then I'm going to turn you loose for your work. All right, so looking at number 1, what is the solubility of NaNO3 at 30 degrees? So we're just going to read that straight off of our chart here. All right, NaNO3 at 30 degrees. All right, and I'm going to go up. Let me get my little pen back so I can mark the point. Sorry, I keep forgetting that I have to restart it each slide. All right, at 30 degrees, I'm going to go up to the line for NaNO3, which is right here. Okay. And so then if I read that off here, roughly 95 grams would be the answer. 95 or 96, depending on how you interpret that. Right? So that's the answer to the first one. At 30 degrees, I can dissolve roughly 95 grams of NaNO3. Number 2, talking about KCl. Notice it says will dissolve in 100 grams. So that's a distraction in there. You don't need that number. The amount of water is just telling you that it matches what's on the graph. So that's all that means, that we have the standard amount of water. Now, the only time that's important is if you have a different amount of water, which we do down in number 4. So we'll come to that. But if I have the standard amount, I can ignore that. All that matters is the temperature. 80 degrees, we're talking about KCl, so 80 degrees interacts with the KCl line right there. KCl and NaCl are hard to tell apart there, so make sure you're careful about the liquids, right? And then I read that off 50 grams. So the solubility of KCl at 80 degrees is 50 grams. That's number 2. Number 3, NH4Cl at 90 degrees. So 90 degrees is my temperature. I'll read that up to NH4Cl right here. And then again, read that off the y-axis, and that's 70 grams. And it's okay to sort of ballpark these. Again, if you're between the lines, or if you think it's not quite at a line, you can be really specific. Like if you think that this point isn't quite 70, you could write 69 grams if you want to. But you can also sort of round off a little bit in the process and say roughly 70 grams, roughly 50. We're not that exact when it comes to solubility. All right, so that's questions 1, 2, and 3. 1, 2, and 3 right there. All we did was find the point and then read this off. And when we're saying the solubility, what we mean is the maximum. So all 3 of these would represent saturated solutions. The curve, the points on the curve are the maximum that can dissolve at that temperature, which means forming a saturated solution. All right, so number 4, slight variation here because we have 200 grams in this problem instead of 100 gram. Now, as you might imagine, that's not difficult to deal with. If I double the amount of water, what do you think that does to the amount of solute that can dissolve? It doubles, right? If I cut the water in half, then I also cut the solute in half. And so you can, as long as you have a fairly easy number to work with, you can sort of scale this up or scale it down in your mind. If it was a difficult number to work with, you could write a proportion, and we'll cross that as we go forward in just a minute. All right, so KNO3 at 40 degrees. KNO3 is up here, right? And so I would call that roughly 62, something like that, right? It's definitely above 60, right? Another person might see it as 61 or 63, and that's fine. All right, so at 40 degrees, I can dissolve 62 grams of KNO3 in 100 grams of water, right? If I have 200 grams, I need to double that value. And so if I can dissolve 62 grams in 100 grams of water, then I can dissolve 124 grams in 200 grams of water. So I simply double that. That's the most common variation of this problem. The other variation that we can get, but it's less common, would be to go the other direction. If I give you an amount of a substance, like salt, for example, and I say, all right, we've got 40 grams of salt. How warm does the water have to be to dissolve that? And then I can go through here and find that somewhere around like in the 95 degree range, that's when water gets warm enough to dissolve that much salt.